Okay, good morning everyone. My name's Oliver Barraclough from SINTEF, so I'm just going to give a quick overview of some of the enabling technologies we have regarding digital twin at SINTEF. So first, just a bit about SINTEF. SINTEF is the largest independent research institute in Scandinavia, and it's actually one of the largest independent research organizations in Europe. So we lie somewhere between academia and industry, delivering applied research and innovation to customers all over the world. So work covers a large range of topics, as you can see, from biotechnology and health to renewable energy and climate research. But of course, in the context of digital twin, it's probably digitalization that's of most importance. However, most use cases have some aspects of these other things in them. So yeah, much of the work we do at SINTEF is very cross-disciplinary, and we can draw on the knowledge of the other departments in SINTEF. So in Change2Twin, SINTEF is represented by the Department of Mathematics and Cybernetics, where we have a focus on developing techniques and developing technologies based on our technical expertise. So major focus for us is mathematical modeling, whether that means geometric modeling or solving mathematical equations that relate to specific engineering problems. So this can involve developing single algorithms or standalone software. We always have a focus on efficient use of computer hardware. So just to give an overview of some of the specific topics we work on related to digital twinning, one major topic we've worked on over the last few years has been volumetric modeling of geometry, so-called VREP. So most computer-aided design models that are used today represent a geometric model by its boundaries, so-called VREP. So this is a bit like modeling an egg by its shell. The interior of the model is not represented explicitly, and this makes it difficult to describe variations in material quality or other aspects, such as stress and strain, that occur non-uniformly within an object. So using volumetric representations enables fusion of the design and analysis stages by using an approach to finite element modeling known as isogeometric analysis. So any of you that are familiar with the design and simulation pipeline will be aware that the process of meshing is very time consuming. It's a major goal of isogeometric analysis to be able to skip this step. In the context of digital twinning, it's also very much preferable to have to only deal with a single representation for the design and the simulation steps, as opposed to separate models. So although there are still open challenges in isogeometric analysis that mean that it can't be directly applied to CAD models, there are some specific use cases where great benefits can be achieved by applying this approach. Another benefit of using volumetric models is in material modeling, particularly functionally graded materials, which are seeing sort of more and more applications thanks to ongoing advances in 3D printing technologies. Another technology we've developed in SINTEF is known as LR splines, or locally refined splines. So this is a specific type of mathematical representation that compactly represents datasets that are dominantly smooth, so mostly smooth, but with maybe local features. So this is done by allowing the underlying mathematical model to be adaptively refined. So this technique was introduced in an academic paper from 2013, and since then it's seen a number of applications in various contexts. So one such example is in terrain models, and we're also looking into digital twins in that context. But this is fully general, and the point here is really that these representations can be used for efficiently querying certain types of data sets, making it possible to track changes over time or to capture data compactly for long-term storage. So just to give a specific use case of digital twinning that we've looked at in Change2Twin, this is some work we've done together with additive industries in the Change2Twin pilot that was mentioned earlier. So additive industries make 3D printing or additive manufacturing machines, and for each 3D printing build, they collect vast amounts of data. So the idea behind the pilot was to capture this data and process it into a complete model that could be queried for geometric deviations or defects that might occur during the process. So the input data here was layered images, one taken at each layer of the build process. We implemented AI and image processing algorithms to extract the geometry of the part, and we also looked into defect detection algorithms. So another thing we implemented was real-time visualization algorithms in a web-based tool that allowed users to inspect the digital twin and make decisions about the process accordingly. Just to mention some of our other activities related to machine learning. First is the use of so-called generative adversarial networks, or GANs, for filling in missing data in digital elevation models. So GANs are a very general approach that can create synthetic data that mimics what you'd expect to see in real life. So in the context of terrain models, what we did was use GANs to learn to fill in either missing buildings or smooth terrain, depending on whether the rest of the scene was urban or rural. But this can be applied in many other contexts, and a specific focus of GANs nowadays is to generate synthetic data when you don't have enough real data available. This is quite a typical problem when training machine learning models for digital twins. So another topic we've worked on is segmentation for reconstructing 3D models of hearts from CT scans. So here we use machine learning based on raw CT data and the labels that are manually made by radiologists to train an artificial neural network. So this is, in a sense, extracting the knowledge from the radiologists to be able to automatically and efficiently perform a job that's actually very labor intensive when done manually. So just before I close up, our technologies can be summarized in the following technology items. We have Go tools, which is a set of C++ libraries that mimic the functionality of a CAD package. It also offers more advanced functionality such as VREPs and isogeometric representations. Go tools is already available in the Change2Twin marketplace, and we're currently working on implementing parts of the functionality as a separate software as a service package. Another tool we develop in SINTEF is IFEM, which is a toolbox for isogeometric analysis covering functionality such as structural mechanics, fluid mechanics, and coupled problems. This is the tool that actually solves the mathematical equations, as opposed to Go tools, which is mainly used for geometric modeling and processing. So IFEM is currently in the process of being listed in the Change2Twin marketplace. As I mentioned, we've also, over the last few years, developed quite a lot of machine learning software, particularly related to images and geometry. Most of these algorithms are tuned to specific use cases, but we can offer consultancy services to help tune these to new scenarios. I'd also like to mention that the vast majority of our software is open source, meaning that it can be tailor-made. We can make tailor-made applications based on the algorithms we develop. So yeah, basically the takeaway I'd like you to get from this talk would be that if you have any geometric or image-based data, then we'd be very happy to look into it and see how we can help you use that in developing your digital twins. So thanks for your attention.
Thank you all.